Welcome back, guys. We're doing more examples of the first derivative test. I think I'm just going to do one example per video because all of the types of problems we're looking at are a little bit different. This is the first derivative test video. These are the types of questions that you might be asked. You might be given a function and somebody might ask you to find the intervals where a function's increasing or decreasing. And then they might ask you to apply the first derivative test to identify and then classify the relative extrema, and then they might ask you to graph f. This example is a little different from the polynomial example we did in the last video because of this x plus 1 in the denominator. The x plus 1 in the denominator makes this a rational function, and rational functions often have vertical asymptotes. Now remember from earlier this semester, we're going to have a vertical asymptote at any x value that would cause the denominator to be 0 when the numerator is not 0. Now we're going to have a problem here when x is equal to -1 because -1 plus 1 is 0. So first we want to find, let's answer these questions, and we'll talk about how that vertical asymptote changes the process a little bit. First, we want to find the intervals where the function is increasing or decreasing. And one of the first things that we should always do with these problems, I didn't do it on the polynomial problem, but I'll tell you why in a minute. The first thing we should do is find the domain of the function. With a polynomial, the domain is all real numbers, so we just assumed that it was all real numbers, but we can't generally assume that. I've got to look at this function and see where is it defined and where is it undefined. Now remember the three things that you have to worry about from college algebra. You want to exclude x values that cause division by 0. You don't ever want to divide by 0. You can't take something and divide it into 0 pieces. It doesn't make any sense. You don't want to take even roots of negative numbers. We can do that, but not in the real number system. Those are complex numbers, and we're not interested in that, not in this class. We also want to exclude x values that cause logarithms of negative numbers or 0. Turns out logs of negative numbers are actually complex numbers as well, which is kind of cool and interesting, I think. But that's for another class. So I'm looking for division, even roots, and logs. And if I don't have any of those, the domain is all real numbers, generally, unless I've got a piecewise function. But if it's just a function defined by a single equation like this, then this is all you have to do to find the implied domain. We don't have any roots, we don't have any logs. The only thing that we might do is accidentally divide by 0. So to find the domain, we're going to take this denominator and set it equal to 0, or set it not equal to 0 and solve for x. So the domain of f is the set of all real numbers x such that the denominator is not equal to 0. This is called set builder notation. And then you'll solve for x. You're really just getting x by itself because you want to know what x is not equal to. I know this is overkill, but there are some other problems where it makes sense to show all this work. X plus 1 is not 0. If we subtract 1 from both sides, we get x plus 1 is not equal to -1. On the number line, that means anything to the left of -1 is fine. That's in our domain. Anything to the right of -1 is fine. So most of the time we don't use set builder notation in calculus class, we use interval notation. We read these intervals from left to right. You go from -infinity to -1, and then -1 to infinity. And because we want the x values to be in this set or this set, we put a union in between them. So that's the domain. All of our critical values for this function have to be in the domain. So if you want to find the intervals where the function's increasing or decreasing, the first thing you need to do is find the domain And after you've found the domain, you need to find the critical values. Those are places where the derivative is 0 or where the derivative is undefined. That's where the function's derivative can go from positive to negative or negative to positive, which would give us the increasing or decreasing behavior that we're looking for. Okay, so we found the domain, and now we want to find the critical values. Critical values or critical numbers, same thing. And the way you do that is you set f prime equal to 0 and solve for x. So those are places where the slope of the graph is 0. And then consider x values in the domain where f prime is undefined. So you're asking yourself the question, are there any x in the domain for which f prime is undefined? So that means you might have a sharp corner. Those are also critical values. Okay, well, we've got a quotient. So in order to find the critical values, I always need to take the derivative, which makes sense, we're in calculus class. When in doubt, just take the derivative. It's probably necessary, at least in this chapter. So we'll take the derivative, and since we have a quotient, we will use the quotient rule. This is my bottom function, that's my top function. Remember that mnemonic? It's low d high. So the bottom function times the derivative of the top function. You can write that out if you want to. If you're ready, if you say to yourself, Miss Townsend, I don't need that step. If you feel ready, go ahead and skip it. If not, just go ahead and write out the rule. It's low d high minus high. You need parentheses for that whole numerator. D low. All divided by low low, bottom function squared. Okay, so that's our derivative. We just need to compute that piece and simplify it. So I've got x plus 1 here, and the derivative of x squared minus 2x plus 1, I'll just take the derivative term by term. Derivative of x squared, you bring the power down, and you multiply by x to the 1 less power. 2 minus 1 is 1. I've got a constant times x. The derivative of a constant times x is just a constant. Derivative of that 1 by itself is just 0. So we're done with that. Minus the quantity, x squared minus 2x plus 1, close parentheses for that quantity. The derivative of x is just 1, and the derivative of 1 is, of course, 0. So this is our derivative. It's just not simplified. In order to simplify it, I think I need to distribute. Oh, actually, maybe there's an easier way. Let's factor. These two terms have a 2 in common, so we can factor that out. And x squared minus 2x plus 1, that factors. Do you recognize that as x minus 1 squared? If you're not sure, just ask yourself, what two numbers multiply to give you 1 that add to negative 2? Well, negative 1 and negative 1 will work. Actually, I don't even need to simplify that further because I want to factor out any common factors here and here. So I'm looking at this and I'm looking at this and I'm saying, what do they have in common? Notice they both have an x minus 1. So I can factor that out from everything. And then I ask myself, x minus 1 times what will give me this? Well, I need the 2 and the x plus 1. And then I say to myself, x minus 1 times what will give me this? Well, I need the negative, and I need another x minus 1. That expression in brackets can be simplified. Let's distribute the 2, distribute the negative, and collect like terms. So I'll have 2 times x plus 2 minus x minus a negative 1. Subtracting a negative 1 is adding 1. And of course, 2x minus x is just a single x, and 2 plus 1 is 3. We're collecting like terms. Okay, that was the derivative. What were we doing again? Oh yeah, we're trying to find the critical values of f. So first we compute the derivative, then we set f prime equal to 0 and solve for x. Remember, these are the places where the slope is 0. So they're like potential hills and valleys, or maybe there's just a little flat spot where it goes from increasing to flat to increasing again, or decreasing to flat to decreasing again. But slope being 0, that's what we're looking for. Well, this fraction is 0 if the numerator is 0. If you don't believe me, you can multiply both sides by x plus 1 squared, and you'll get the numerator equals 0 times x plus 1 squared. And I mean, I always just think about it. The only way a fraction is 0 is if the numerator is 0. I'll have 0 divided by something equals 0. That's the only way. If this is anything other than 0, we're not getting 0 out of this. Okay, so if this times this is 0, that means either the first factor is 0 or the second factor is 0. Take each of those and solve for x. Okay, so we've got two critical points. X equals 1 and x equals -3. Now we have to ask ourselves, are there any x in the domain for which f prime is undefined? Well, look at f prime. There it is. Well, we'll have a problem when the denominator is 0, but that's x equals -1, right? X equals -1 is not in the domain. So there are no other critical values. We've just got these two critical values, critical points, same thing. Okay, and now we're going to use those to as tick marks on our number line. So we're going to do our sign analysis of f prime now. That's going to allow us to determine where the function's increasing and decreasing. So you draw a number line, and you need to put these critical points on the number line. So we're going to use the critical points and any x values for which f is undefined as tick marks on the number line. So remember, f was undefined at -1, and we know that that would cause the denominator to be 0 when the numerator isn't, so that's a vertical asymptote. And then -3 and 1 also have to be on the number line, so we'll have -3 over here, -1 here, and x equals 1 over here. So actually I have 4 intervals, but I want to be very clear that -1 is not a potential min or a max. It's an asymptote, so I'm just going to draw this asymptote here just to remind myself that there's a vertical asymptote at x equals -1. Okay, and after we've put our critical values and our asymptote on the number line, then we'll put the factors of f prime down here. F prime was x minus 1 times x plus 3. And then it was divided by x plus 1 squared. I've got 4 intervals. Now I think I'll do x plus 1 squared first. If x is -1, that's 0. But x isn't -1. We're talking about these other intervals. For any other x value, x plus 1 squared is positive, because I take a number, I square it. I always get a positive number except for when I get 0, and that 0 is on that vertical asymptote. Okay. So this is positive all the time. So it's positive on that interval, that interval, that interval, and that interval. Now to find the sign of x plus 3 and x minus 1 on these 4 intervals, I'll just pick an x value on each interval. So this is -∞ to -3. I'll pick x equals -4 on this interval, because -4 is between -∞ and -3. Negative 4 minus 1 is negative 5, so that's negative. Substitute in x equals negative 2 for this interval. Negative 2 minus 1 is negative 3, so that's negative. Between negative 1 and 1, pick any x value you want. I'll probably pick 0 because it's easy to plug in, right? 0 minus 1 is negative 1. And if I pick an x value that's greater than 1, say x equals 2, 2 minus 1 is positive 1. Notice that this goes from negative, 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 then to positive. And it goes from negative to positive at x equals 1. That's the x value that would make this factor 0. That will always happen. The x value that causes this factor to be 0 is where it's going to change signs. If you've got like mx plus b as a factor, okay? It's just a linear factor like that. It's like the line y equals x minus 1. It's going to be below the x-axis until we get to here, and then it crosses, and then it gets above the x-axis. Okay, anyway, instead of thinking about the graphs, this is negative, 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 and then at x equals 1, it becomes positive. Let's do the same thing with x plus 3. Substitute in negative 4 here. Negative 4 plus 3 is negative 1. Negative 2 on that interval. Negative 2 plus 3 is positive 1. Plug in 0 in that interval. 0 plus 3 is positive. Plug in 2. 2 plus 3 is 5, which is positive. Again, it changes from negative to all these positives at x equals negative 3. That's the x value that would cause that to be 0. Okay, f prime is it's this times this divided by this. So I've got a negative times a negative divided by a positive, so f prime is positive. Over here, I have a positive times a positive, or a negative times a positive, that's negative. A negative divided by a positive is a negative. Then I've got a negative divided by, or a negative times a positive is a negative. A negative divided by a positive is a negative. And of course, multiply two positives and divide by a positive and you get a positive. Okay. So now I know the intervals where f prime, or where the function is decreasing and increasing. It's increasing wherever the slopes are positive, and the slope is positive when the derivative is positive. So it's increasing over here. And then on the intervals where the slopes are negative, that means the derivative is negative. Well, that's where it's decreasing. So it's increasing where the slope is positive, decreasing where the slope is negative. So when they ask you to find the intervals where this function is increasing or decreasing, you make your sign chart, you list the factors of f prime, find the sign of each factor on each interval, make sure you include any asymptotes, and then you just multiply those signs together or divide, and that's going to give you the sign of f prime. So the original function f is decreasing on the interval from negative 3 to negative 1. We're reading those number lines. We're reading that interval from left to right, smallest to largest, and then negative 1 to 1. Now don't tell me it's decreasing from negative 3 to 1 because there's an asymptote there. There's actually two different pieces of our graph, so we need two separate intervals. So negative 3 to negative 1 and then negative 1 to 1. And then it's increasing on the other side, or on the other intervals, excuse me. Increasing over here, there's an implied negative infinity there because of that arrow. Negative infinity to negative 3, it's increasing. And 1 to positive infinity, it's increasing. And you might use a union, you might not. I'm not sure what WebAssign wants. Okay, so we've got our little sign chart for that. We've got increasing, decreasing, we're good to go. Okay, now what else were we asked? Apply the first derivative test to identify and classify any relative extrema, and then we want to graph the function f. Okay. Well, we've got two critical points, negative 3 and 1. Do we have a max here or a min here? Or max here or a min here? I think you can just look at the arrows and tell. Can't you tell that that's going to have to be a max? The slope goes from increasing to a 0 slope to decreasing. So we'll have to have a max there. And here the slope goes from, or the function goes from increasing to 0, having a 0 slope to decreasing, or positive slope to 0 slope to negative slope. Or over here, it goes from decreasing, so negative slope, to 0 slope, to positive slope. So we've got a min. Max there, min there. Now, you don't say x equals -3 is the max. If somebody asks you for the maximum height of, let's say, a falling object, you don't tell them what time it's at the maximum height. You give them the height, right? So the maximum, the relative maximum here is the y value that goes with x equals -3. And I've got more examples for another video. We need more paper. Okay. Okay, so we have a relative max of f of -3, whatever that happens to be. And our function was x squared minus 2 times x plus 1 all over x plus 1, just using placeholder notation. You don't have to do this if you don't need to. So we get 9 plus 6 plus 1 over -2. So we've got 16 over -2, which is -8. That's our relative max. Okay, and we get a relative min so we have a relative max of -8, and it occurs at x equals -3. We have a relative min, and the relative min is the y value. It's f of 1. So you have 1 squared minus 2 times 1 plus 1 over 1 plus 1. So I've got 1 minus 2 plus 1 over 2. The numerator is 0, so we get 0. Okay. Now we want to put all of these pieces together and graph the function. Well, what do we know? Well, we know we've got an asymptote at x equals -1. And we know that we have a relative max at x equals -3, and that maximum value is -8. I know it doesn't seem like much of a max, but I guess it is. This is not to scale. And over here, what do we know over here? We know that at x equals 1, we've got a relative min of 0. Okay, and then what else do we know? Well, we know where the function's increasing and decreasing. And we also know we've got an asymptote here, so we know that this function is going to get very close to this vertical line, x equals -1. So we know that it's increasing on -∞ to -3, decreasing on -3 to -1, decreasing again on -1 to 1, and increasing again on 1 to infinity. So what does that mean? It's increasing until we get to -3, so it's going to look like this. And then it's decreasing from -3 to -1, and it's approaching an asymptote, so maybe it looks like that. Okay. And then, let's see, what else do we know? I guess I could find an y-intercept. When x is 0, we get 1. And we know on the interval from -1 to 1, so that's this interval, the function's decreasing. and it's got an asymptote, so it's going to be decreasing. And then at x equals 1, we get a min of 0, and then it's increasing again. Now this is very much not to scale. I've done a poor job of graphing this because of just my desire not to draw 8 tick marks going down like this. But this function f of x is x squared minus 2x plus 1 over x plus 1. Notice that the degree of the numerator is 1 more than the degree of the denominator. What that means is that this function actually has what's called a slant asymptote. So there's going to be a line like this that the graph actually gets really close to. I didn't do a very good job graphing it, but it's going to look kind of like that. Roughly. Very, very, very roughly. But the original graph, the one I first drew, satisfied all of this. It was increasing, had a max, then decreasing, asymptote, decreasing, then it had a min, and then it was increasing again. And then just using a little bit of pre-calculus knowledge, I knew it also had a slant asymptote. Your graph doesn't have to be perfect, it just has to have all of this behavior. So it has to have the right vertical asymptote, the right relative max and min, and the right intervals where it's increasing and decreasing.